Now, in this lecture, we will find out the radius of a circle using two different methods. In the drawing, we have a circle. We know that the center of this circle is at this point O. We also know that the length from side AB is 6 units, the length from side AD is 18 units, the length of side BC is equal to 13 units. This angle BAD equals to 90 degrees. This angle ABC equals to 90 degrees, and our mission is to find out the radius of this circle. So first of all, we'll do a construction from point C. We draw perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction, we actually created the quadrilateral ABCE. This quadrilateral ABCE is 1, 2, 3 right angles. The sum of right angles is 270 degrees plus the size of the fourth angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the fourth missing angle must be also equal to 90 degrees in order to complete the sum of the angles to 360 degrees. In this quadrilateral, this angle must be equal to 90 degrees. And because of the fact that quadrilateral ABEC has 4 right angles, therefore quadrilateral ABEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. But it is given us the question that AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But it is given us the question that BC equals to 13 units, therefore AE will be also equal to 13 units. What is the length of line segment ED? The length of line segment ED, it will be equal to AD minus AE. Again, AD minus AE equals to ED. That is to say, ED equals to AD, that is 18, minus AE, that is 13. 18 minus 13 is 5. So in conclusion, we found out that the length of line segment ED equals to 5 units. In the next step, we will join points D and C together by a straight line. By joining points C and D, we actually created the right green triangle EDC. In the next step, we will implement the Pythagoras theorem on the right green small triangle EDC. According to the Pythagoras theorem, here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green small triangle is DC, therefore the square of the hypotenuse is DC squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to EC squared plus ED squared. I'll repeat again. According to the Pythagoras theorem, on the right green small triangle ECD, DC square equals to EC square plus ED square. So DC square, that is the square of the hypotenuse, equals to EC square. EC equals to 6, so EC square equals to 6 squared, that is 36. Plus ED square. ED equals to 5, therefore ED square equals to 5 squared, that is 25. So in conclusion, we found out that DC square equals to 36 plus 25. That is to say, DC square equals to 36 plus 25 is 61. So this is equals to 61. We take out of this equation and we get that this equals to the square root of 61 units. Here the hypotenuse DC of the small green right triangle, DC equals to the square root of 61 units. In the next step, we will join points B and D together by a straight line. By joining points B and D, we actually created the right triangle, triangle ABD, the right weak triangle, triangle ABD. So we will implement the Pythagoras theorem on the right triangle, triangle ABD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus AD squared. Again, according to the Pythagoras theorem on the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse in the right triangle ABD, equals to AB squared. If AB equals to 6, so AB squared is 6 squared, it is 36, plus AD squared. If AD equals to 18 units, AD equals to 18 units, therefore AD squared is equal to 18 squared, that is 324. In conclusion, we found out that BD squared equals to 36 plus 324. That is to say, BD squared equals to 36 plus 324 is 360. Here we'll substitute 360 by 36 times 10, so we get that BD squared equals to 36 times 10. Here we'll take a root out of this equation and we get that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we can take 36 out of the root. We do it now and we get that BD equals to 6 times square root of 10. In conclusion, we found out that the length of the hypotenuse BD it is equal to 6 times square root of 10 units. In the next step, we find out the area of the triangle BDC. We find out the area of the green triangle, triangle BDC. Here the squared brackets is the same for the area. It means the area of triangle BDC. The area of any triangle is equal to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of triangle BDC will be equal to the base. We'll choose the base as BC. So I substitute the base by BC times the height over 2. So we'll extend side BC by a straight line, and from point D we'll draw perpendicular on the extended BC. So this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point D in the extended BC as F. Here you can see here that DF is perpendicular to the extended BC, therefore DF is the height to the base BC. And DF is the height to the base. In the next step we find out the value of the height. Actually we created here quadrilateral ABDF. Inside quadrilateral ABDF we have 1, 2, 3 right angles. Therefore the fourth angle, this fourth angle must be also equal to 90 degrees. Therefore in quadrilateral ABDF we have 4 right angles, therefore quadrilateral ABDF is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to DF. Okay? AB, so I write it down. First of all, quadrilateral ABDF is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. In rectangle ABDF. AB equals to DF. But we have already, it is given us the question that AB equals to 6. So we can write here AB equals to 6. And from this equation 6 equals to AB equals to DF. And we derive that DF is also equals to 6 units. Okay, so we found out that the height to the base it is equal to 6 units. Now we can easily find out the area of the green triangle BDC. So the area of the green triangle BDC will be equal to the base. We choose the base as BC, and the length of BC is 13 units according to what is given us the question, times the height. We just right now found out that the height, dF equals to 6 units, so we can substitute the height by 6 over 2. So the area of triangle BDC will be equal to 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of the green triangle BDC equals to 39 square units. Okay. In the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. Okay, this will be actually rule number 1. Rule number 1 is to in any circle, so the circle that I draw could be any circle. The center of this circle is at this point O, inside this circle we have triangle ABC that is blocked by this circle. This is triangle ABC. A triangle is blocked by a circle only and only if all the three vertices lie on the circle. Here, this vertex lies on point A of the circle, this vertex lies on point B of the circle, and this vertex lies on point C of the circle. Therefore, it is triangle ABC. It is definitely blocked by this circle. So I write the rule number 1 down. So if a triangle is blocked by a circle, that is to say all of its three vertices lying on the circle, we define the radius of this circle as capital R. Here OM, that is the radius of the circle, equals to capital R according to our definition. Then the radius of this circle that blocks the triangle, here the length of side AB equals to A units, side BC equals to B units in its length, and side AC equals to C units in its length. Then the length of the radius that blocks the triangle will be equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other, over 4 times the area of triangle ABC. Okay. Again, whenever a triangle is blocked by a circle, like in this drawing, all the three vertices of triangle ABC are lying on the circle. Then the radius of this circle that blocks the triangle will be equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other over 4 times the area of this triangle, triangle ABC. So we can implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC that is blocked by this circle. Why it is blocked by this circle? Because this vertex lies on point B of the circle, this vertex lies on point C of the circle, and this vertex lies on point D of the circle. Therefore, we can use the rule number 1. According to, so I write it down, triangle BDC, the green triangle, is blocked by the circle and therefore we can use rule number 1, and therefore according to rule number 1, capital R, we define the radius of this circle as capital R. Here OM, that is the radius of the circle, equals to capital R. Capital R equals to the multiplication of the side lengths of the triangle by each other, that is to say BC times CD times DB, over 4 times the area of the green triangle, triangle BDC. repeat again. Because of the fact that the green triangle BDC is blocked by the circle, you can implement here rule number 1. And according to rule number 1, the radius of this circle that blocks the triangle that we defined as capital R will be equal to VC times CD times DB, that is the multiplication of the side depths of the green triangle by each other, over 4 times the area of the green triangle BDC. So capital R is equal to BC equals to 13 units, times CD equals to the square root of 61 units, and DB equals to 6 times square root of 10 units. All, again, I'll repeat again, DB equals to 6 times square root of 10 units, CD equals to the square root of 61 units, and BC equals to 13 units, over 4 times the area of triangle BDC, and we have already found out that the area of triangle BDC equals to 39. So actually that is the answer to the question. That is to say the radius of this circle is equal to this expression. We'll simplify this expression. That is to say we'll divide both the numerator and the denominator of this expression by 13. In the numerator we have 13, and 13 over 13 is 1. So 13 will get cancelled, and we are left only with the square root of 61 times square root of 10 times 6 over 4 times 39. 39 over 13, 39 over 13 is 3. So, and there 4 times 3 is 12. So in conclusion we found out that the radius of and this circle, it is equal to the square root of 61 times the square root of 10 times 6 over 12. 4 times 3 is 12. Here we divide both the numerator and the denominator of this expression by 6, and we get that the radius of the circle equals to the square root of 61 times the square root of 10, and 6 over 6 is 1, so 6 will get cancelled, and 12 over 6 is 2. So the radius of the circle equals to the square root of 61 times square root of 10 over 2. That is to say the radius of the circle here, according to the algebraic identity, that the square root of A times square root of B equals to the square root of A times B, we get that the square root of 61 times the square root of 10 equals to the square root of 61 times 10 over 2. So the radius of the circle equals to the square root of 61 times 10 is 610 over 2. Okay. So we actually found out that the radius of this circle, it is equal to either the square root of 610 over 2 units, or in terms of numbers it is equal to 12.349 units. Okay, so we finished with the first method. In the next step I will present to you the second method. Our mission is to find out the radius of this circle. Okay, so we'll do the first step, the same thing that we already done in the first method. That is to say, from point C we draw perpendicular on AD. So this angle equals to 90 degrees. And this angle it is also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. Here we actually, by doing this construction, created quadrilateral ABEC. Inside quadrilateral ABEC we have three right angles, therefore the fourth angle must be equal to 90 degrees. And therefore quadrilateral ABEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC, but AB equals to 6, therefore EC will be also equal to 6. According to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that BC equals to AE. But it is given as the question that BC equals to 13, therefore AE will be also equal to 13. And here ED equals to AD minus AE. AD minus AE is 18 minus 13, that is 5. Okay, we did all those things in the first method. Then in the second method, we will do the construction, that is to say, from the center of the circle, that is to say, from point O, we will do perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle it is also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as capital N, and we define the touching point of the perpendicular from point O and AD as M. Okay, in the next step I will present to you a new rule, and we will implement the new rule in our drawing. So according to the new rule, that will be actually rule number 1. Rule number 1 is drawn in any circle, so the circle that I will draw will be any circle. This point is the center of the circle, we define it as point O. And we have here chord BC. This is chord BC, that could be any chord. And from the center of the circle, that is to say from point O, we will go perpendicular on BC. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as M. So from the center of this circle, that is to say from point O, we drew perpendicular OM on BC. Okay. So I write it down. A perpendicular from the center of the circle this is to say point O. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . towards any chord. In our case, we are talking about the chord BC, that could be any chord. Bisect the chord. Bisect the chord. That is to say, BM equals to MC. BM equals to MC. So whenever you draw perpendicular from the center of the circle, in this case is point O, towards any chord, it will bisect the chord. In this case we draw from point O, that is the center of the circle, a perpendicular OM towards chord BC, therefore it bisects chord BC. That is to say, BM equals to MC. We actually can implement rule number 2 in our drawing. Why? Because in our drawing we have from the center of this circle, that is to say point O, we have perpendicular ON towards BC, towards chord BC. Okay. From the center of the circle, that is to say point O, we have perpendicular ON towards chord BC. Therefore, we can implement here rule number 2, and according to rule number 2, the perpendicular ON bisect chord BC. That is to say, BN equals to NC. BN equals to NC according to rule number 2. Okay. Because of the fact that we have a perpendicular ON from the center of the circle, that is to say from point O towards chord BC, therefore it must bisect chord BC. That is to say, BN equals to NC. Okay. In the next step, we will focus on quadrilateral ABMN. This quadrilateral, inside quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, and therefore, in quadrilateral ABMN, we have 4 right angles. Therefore, quadrilateral ABMN is a rectangle. So I write it down. Quadrilateral ABMN is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Likewise, we will focus on quadrilateral MNEC, this quadrilateral, the lower quadrilateral. In quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. That is to say, inside quadrilateral MNEC, we have 4 right angles. Therefore, quadrilateral MNEC is a rectangle. I write it down. Quadrilateral MNEC is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize what we did until now. We actually found out that according to rule number 2, Bn equals to Nc, and we also found out that Bn it is also equal to Am, so we can write here Bn equals to Am, and we also found out that Nc equals to Me, so we can write here that Nc equals to Me, and from this long equation Am equals to Bn equals to Nc equals to Me, we will derive that Am equals to Me. Am equals to Me. Okay. Usually in the drawing you can see that here side Am equals to side Me. Okay. In the next step, we'll extend line segment DA until it touches the circle, and we'll define the touching point of the extended line segment DA and the circle as F. Here, by doing this construction of this extension, we created chord FD. This is called FD. Actually, we draw perpendicular from point O towards chord BC. That is to say, ON is perpendicular. So ON is a perpendicular, it must be a straight line. So we know that ON is a straight line, and so if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to the rule that I mentioned. Therefore the missing angle, this angle must be equal to 90 degrees. Likewise, if we focus on the lower side of the straight line ON at point M here the sum of the angles must be equal to 180 degrees according to the same rule. Which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here, this angle, must be also equal to 90 degrees. We actually have here line segment OM that exists from the center of the circle that is perpendicular to chord FD. So I write it down. From the center of the circle, that is to say from point O, we have line segment OM that is perpendicular to chord FD. Whenever you have from the center of the circle perpendicular to any chord, and especially chord FD, it must bisect the chord. That is to say, chord OM, line segment or perpendicular OM bisects chord FD, according to rule number 2. That is to say, FM equals to MD. According to rule number 2, FM equals to MD. Okay. FM equals to MD. What is the value of FM? It is very easy to see that FM equals to FA plus AM. FA plus AM. And what is the value of MD? From drawing it is very easy to see that MD equals to, here MD equals to ME plus ED. ME plus ED. So we actually found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. AM equals to ME. Here, AM equals to ME. That is to say, we can cancel those two line segments because they are equal to each other. We cancel them out and we left only with FA that is equal to ED. FA equals to ED. That is to say, FA equals to ED. Again, FA equals to ED. But we have already found out that ED equals to 5 units, so we can write here ED equals to 5, and from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. Okay. In the next step, we'll extend side BA until it touches the circle. And we will define the touching point of the extended side BA and the circle as point P. Here we can implement the old rule number 2 in our circle. I will remind you what is the meaning, what is rule number 2. This is the old rule number 2. According to old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have chord FD that intersects with chord PB at point A. Again, chord FD intersects with chord PB at point A. I'll write it down. In our original drawing, we have chord FD that intersects with chord PB at point A. Chord FD intersects with chord PB at point A. Point A is the intersection point between the two chords. Therefore, according to the old rule number 2, we'll get that FA times AD equals to PA times AB. FA times AD equals to PA times AB. According to the old rule number 2. Okay. FA equals to 5, AD equals to 18 units, PA is the missing line segment, so we leave it as it is, and AB equals to 6 units. In conclusion, we found out that according to the old rule number 2, 5 times 18 equals to PA times 6. Here we divide this equation by 6 and we get that the missing line segment PA equals to 5 times 18 over 6. So PA equals to 18 times 6 is 3 and 3 times 5 is 15. So PA equals to 15 units. You can write down in the drawing that PA equals to 15 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. According to the new rule that I will define as rule number 4, so before I draw the rule, I'll explain what is the meaning of rule number 4. Rule number 4 states that whenever you have two chords that are perpendicular to each other, then a certain equation is true. Okay, so I will draw the drawing for the new rule, rule number 4. Point O is the center of the circle. Here we have chord AB, this is chord AB. That is perpendicular to chord CD. Here. That is to say, they create with each other 90 degrees at the intersection point. Here, this angle equals to 90 degrees. That is to say, they are perpendicular to each other. We define the touching point or the intersection point as point E. You can see here that chord AB is perpendicular to chord CD. We define the radius of this circle as capital R. That is to say, OM equals to capital R, according to our definition. So I write down the new rule, rule number 4. If chord AB, this is chord AB, intersects with chord CD, this is chord CD, at 90 degrees at point E. Point E is the intersection point between the two chords. Actually, you can also write down that if two chords are perpendicular to each other, it is exactly the same thing. Okay? Then the following equation will be true. That then 4 times capital R square, capital R is the radius of the circle, will be equal, so this is a way to find out the radius of the circle, will be equal to AE squared plus EB squared plus CE squared plus ED squared. I repeat again, if two chords are perpendicular to each other, like in this drawing, chord AB is perpendicular to chord CD. Why? Because they create between them at the intersection point 90 degrees. Then the following equation is true. So if two chords are perpendicular to each other, the following equation will be true. Capital R is the radius of the circle, so 4R squared equals to AE squared plus EB squared plus CE squared plus ED squared. Okay? So actually we can implement rule number 2, rule number 4, this rule number 4 in our drawing. Why? Because in our drawing we also have two chords that are perpendicular to each other. Here chord FD is perpendicular to chord PB. Why? Because of the fact that they create between them at the intersection point 90 degrees. The intersection point is point A between the two chords, and they create between them 90 degrees. Therefore, they are perpendicular to each other. That is to say, we can implement here rule number 4. So I write it down. In our drawing, we have chord FD. This is chord FD. Is perpendicular to chord PB. Again, chord FD is perpendicular to chord PB. Why they are perpendicular to each other? Because of the fact that the intersection point, they create here 90 degrees. This again equals 90 degrees. Therefore, we can implement it rule number 4. And according to rule number 4, here we will define the radius of this circle as capital R. Here, M is the point on the circle itself, therefore OM equals to capital R. Therefore, according to rule number 4, 4R squared, 4 times capital R squared, will be equal to FA squared plus AD squared plus PA squared plus AB squared. I repeat again, because of the fact that chord FD in our original drawing, chord FD is perpendicular to chord PB, we can implement here rule number 4, and according to rule number 4, 4 times R squared, or capital R squared, capital R is the radius of the circle, equals to FA squared plus AD squared plus PA squared plus AB squared. Repeat again, chord FD is perpendicular to chord PB in our original drawing, therefore we can implement here rule number 4. According to rule number 4, 4 times capital R squared, capital R squared, capital R is the radius of the circle, equals to FA squared plus AD squared plus PA squared plus AB squared. So 4R squared equals to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18 units, therefore AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. In conclusion, we found out that according to rule number 4, 4R squared, when R is the, or capital R is the radius of the circle, equals to 25 plus 225 is 250, plus 324 plus 36 is 360. In conclusion, we found out that 4R squared equals to 250 plus 360. That is to say, 4R squared equals to 250 plus 360 is 610. So 4R squared equals to 610. We divide this equation by 4, and we'll get that R squared equals to 610 over 4. Here we'll take a root out of this equation, and we will get that capital R equals to the square root of 610 over 4. That is to say, capital R equals to the square root of 610 over the square root of 4 is 2, so you can take 4 out of the root. In conclusion, we found out that the radius of this circle, the radius that we are looking for, that is to say capital R or M, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finished with the second method. In the next step, I will summarize the lecture. We'll start with the first method. So in the drawing we have a circle. We know that the center of this circle is at this point O. The length of line segment AB equals to 6 units. Line segment AD equals to 8 units in its length. Line segment BC equals to 13 units in its length. This angle BAD equals to 90 degrees, and this angle ABC equals also to 90 degrees. Our mission is to find out the radius of this circle. Here you can see the radius of this circle is defined, the definition is equal to capital R. That is the length of line segment OM. So in the first step we actually did a construction, that is to say from point C we draw perpendicular on AD. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction, we created here quadrilateral ABCE. This quadrilateral ABCE has 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the missing fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, the missing angle, this angle, must be equal to 90 degrees. Actually, we found out that inside this quadrilateral ABEC, we have 4 right angles. Therefore, quadrilateral ABCE is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But it is given us the equation that AB equals to 6 units. Therefore, EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But it is given us the equation that BC equals to 13 units. Therefore, AE must be also equal to 13 units. What is the length of line segment DE? It is very easy to see from the drawing. That DE equals to AD minus AE. Again, AD minus AE equals to ED. AD equals to 18 units. AE equals to 13 units. Therefore, AD minus AE is 13. 18 minus 13, that is 5. So we found out that ED equals to 5 units. In the next step, we joined points D and C together by a straight line. By joining points D and C, we created the small green triangle ECD. Then we implemented the Pythagoras theorem on the small green triangle ECD. By PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the small green triangle ECD is DC, therefore the square of the hypotenuse is DC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. In conclusion, the right green small triangle ECD, according to the Pythagoras theorem, DC square equals to EC square plus ED square. That is to say, DC square equals to EC square. EC equals to 6, therefore EC square is equal to 6 squared, that is 36. Plus ED square. ED equals to 5. Therefore, ED square is 5 squared, that is 25. In conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61. So DC square equals to 61. We took a root out of this equation and we found out that DC equals to the square root of 61 units. Here, the hypotenuse DC equals to the square root of 61 units. In the next step, we joined points B and D together by a straight line. By joining points B and D, we created the right triangle ABD, and we implemented the Pythagoras theorem on this right triangle ABD. According to the Pythagoras theorem, in the right triangle ABD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB square plus AD square. So here in the right triangle ABD by PT, BD square equals to AB square plus AD square. So BD square, that is the square of the hypotenuse in the right triangle ABD, equals to AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. Plus AD squared. AD equals to 18 units, therefore AD squared equals to 18 squared, that is 324. In conclusion, we found out that BD squared equals to 36 plus 324. 36 plus 324 is 360. So we found out that BD squared equals to 360. Then we substituted 360 by 36 times 10, so BD squared equals to 36 times 10. We took a root out of this equation, and we found out that BD equals to the square root of 36 times 10. Here we can take out 36 out of the root. Why? Because the square root of 36 is 6. We did it, and we got that BD equals to 6 times square root of 10. Here, the hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. In the next step, we found out the area of the green triangle BDC. This green triangle BDC. Actually, the area of any triangle is equal to the base of the triangle times the height to the base over 2. Here, I must emphasize that the height to the base must create 90 degrees with the base. So the area of triangle ABC equals to the base. We choose the base of the green triangle BDC as BC times the height. Again, the height must create 90 degrees with the base, all divided by 2. Okay, so in the next step, we must find out the height of this green triangle, triangle BDC. So, in the next step, we actually extended side BC by a straight line, and then from the vertex D, we do perpendicular on the extended BC. We define that, so that this angle equals 90 degrees and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point D and the extended BC as F. So by doing this construction, we created here quadrilateral ABFD. This is quadrilateral ABFD. Inside quadrilateral ABFD, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABDF has 4 right angles, and therefore quadrilateral ABDF that has 4 right angles, it is a rectangle. Okay, here, quadrilateral ABDF is a rectangle because it has 4 right angles. Okay, but we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. AB equals to DF. But it is given us in the question that AB equals to 6 units. So we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF. We will derive that DF is also equals to 6 units. That is to say, the height DF equals to 6 units. Now we can easily find out the area of this green triangle, triangle BDC. According to the formula, the area of the green triangle BDC equals to the base times the height over 2. We choose the base as BC, but BC equals to 13 units, so we can substitute BC by 13 times the height. We just right now found out that the height DF equals to 6. So we can substitute the height by 6 or divided by 2. So the green triangle BDC equals to 16 times 6 over 2. 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of the green triangle BDC equals to 39 square units. Okay. In the next step, I presented to you a new rule. That is actually rule number 1, and we implemented rule number 1 in our drawing. So here, if a triangle is blocked by a circle, you can see here that this triangle ABC is blocked by this circle. Why it is blocked by this circle? Because of the fact that all the 3 vertices of this triangle are touching the circle. This vertex touches the circle at point A, this vertex touches the circle at point B, and this vertex touches the circle at point C. Only and only if all the three vertices are touching the circle, only then you can say that the triangle is blocked by a circle. Otherwise, the triangle is not blocked by the circle. Okay, so you can see here that indeed this circle blocks triangle ABC. You know that the length of side AB is A units, the length of side AC is units, and the length of side BC is B units. Okay, and the radius of this circle is OM, that is equal to capital R according to our definition. So whenever you have a triangle that is blocked by a circle, you can use this formula in order to find out the radius of the circle that blocks the triangle. And the radius of this circle that blocks the triangle, that is to say capital R, will be equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other, the triangle that is blocked by the circle, over 4 times the area of this triangle that is blocked by the circle. That is to say over 4 times the area of triangle ABC. Okay, so we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC. First of all, the green triangle BDC is blocked by this circle. Why? Because of the fact that this vertex touches the circle at point B. This vertex touches the circle at point C, and finally this vertex of the triangle touches the circle at point D. Therefore, you can say for sure that triangle BDC, the green triangle, is blocked by this circle. And for that reason, we can implement here rule number 1. Okay, here triangle ABC is blocked by the circle, and therefore we can implement here rule number 1. According to rule number 1, the radius of this circle, that is to say capital R, will be equal to BC times CD times TB, BC times CD times BD, that is the length of the sides of the triangle, or the side lengths of the triangle, over 4 times the area of the green triangle, triangle BDC. BC equals to 13. DC equals to the square root of 61, and BD equals to 6 times square root of 10. Okay, so we substitute here, we substitute them by the values of each of them, and all divided by 4 times the area of the green triangle BDC, and we've already found out that the area of the green triangle BDC equals to 39 square units. Okay, so we actually found out that is the answer to the question, that is the radius of this circle. In the next step, we actually simplified this expression by dividing both the numerator and the denominator by 13. We divided the numerator by 13, therefore 13 over 13 is 1, so 13 will get cancelled, and we left only with square root of 61 times square root of 10 times 6 over 4 times 39. So it is 4 times, and 39 over 13 is 3. In conclusion, we found out that the radius of the circle equals to the square root of 61 times square root of 10 times 6 over 4 times 3. 4 times 3 is 12. So in conclusion, we found out that the radius of the circle equals to the square root of 61 times square root of 10 times 6 over 12. We divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so 6 will get cancelled, and we left only with square root of 61 times square root of 10 over 12 over 6 is 2. So in conclusion, we found out that the radius of this circle, the radius of this circle capital R, equals to the square root of 10 times square root of 61 over 2. According to the algebraic identity, that the square root of A times square root of B equals to the square root of A times B, we will get that the square root of 61 times square root of 10 equals to the square root of 61 times 10. all divided by 2. And 61 times 10 is 610. In conclusion, we found out that the radius of this circle, that is to say capital R, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the first method. In the next step, I actually presented to you the second method to find out the radius of this circle. In the second method, actually in the first step, we did all the things that we have already done in the first method, that is to say, from point C we drew perpendicular on AD, that is to say this angle equals 90 degrees and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point C as E. By doing this construction, we created quadrilateral ABCE that has 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral ABEC has 4 right angles. Therefore, quadrilateral ABCE is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6, therefore EC also equals to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that BC equals to AE. But BC equals to 13 units according to what is given us in the equation. Therefore, AE must be also equal to 13 units. Then we found out the length of line segment ED. ED equals to AD minus AE. AD is 18, AE is 13. 18 minus 13 is 5. So ED equals to 5. Until now, we did all the things here that we have already done in the first method. Then we continued with the second method. In the second method, from the center of the circle, that is to say from point O, we do perpendicular on chord BC. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as capital N. And we define the touching point of the perpendicular from point O, that is the center of the circle, and AE as M, or capital M. Then I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, the perpendicular from the center of a circle, in this case the center of the circle is at point O, the perpendicular from the center of the circle towards any chord bisect the chords. So we do perpendicular from the center of the circle, that is to say from point O towards chord BC, and according to this rule, rule number 1, the perpendicular OM, first of all this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So the perpendicular OM is not only perpendicular, but it is also bisect chord BC. That is to say BM equals to MC. Okay, so the perpendicular from the center of the circle towards any chord bisects the chord. In this case, the perpendicular OM bisects chord BC, that is to say BM equals to MC. We can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the perpendicular ON towards chord BC. So because of the fact that from the center of this circle we have perpendicular towards chord BC, according to rule number 1, it must bisect the chord. That is to say, BN equals to NC. So, repeat on it, from the center of the circle, that is to say from point O we have perpendicular ON towards chord BC. Again, from the center of the circle, that is to say from point O, we have perpendicular ON on chord BC. Okay, this is perpendicular, ON is perpendicular. Why? To BC, because this angle equals to 90 degrees and this angle equals to 90 degrees. Okay, so we have perpendicular from the center of the circle ON towards chord BC. According to rule number 1, it bisects chord BC. That is to say BN equals to NC. Okay, so BN equals to NC according to rule number 1 actually. According to rule number 1. Okay, again, because of the fact that from the center of the circle, that is to say from point O, we have perpendicular ON on BC, it must bisect chord BC. That is to say BN equals to NC according to rule number 1. BN equals to NC according to rule number 1. Then we focused on quadrilateral A, B, M, N. In this quadrilateral, inside this quadrilateral, we have 1, 2, 3 right angles. Here we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral A, B, M, N is a rectangle. Repeat again, quadrilateral A, B, M, N is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say AM equals to BN. AM equals to BN. Okay? Then we focus on quadrilateral MNEC. In quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral MNEC is a rectangle. And again, quadrilateral MNEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can actually summarize and say what we have already found until now. We have already found out that according to rule number 2, BN equals to NC. But BN, it is also equals to MA. So we can write here that BM equals to MA. And we also found out that NC it is also equals to ME. So we can write here that NC equals to ME. So in conclusion, we found out that AM equals to BN equals to NC equals to ME. From this long equation, we can derive that AM equals to ME. AM equals to ME. So here side AM equals to side ME. Okay. Then we actually extended line segment DA until it touches the circle as point F. Point F is the touching point of the extended line segment DA and the circle. We actually in this way created chord FD. Okay? And here from point O, we go perpendicular ON on BC. ON is perpendicular, so ON is a perpendicular, it is absolutely a straight line. And we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. Okay. According to the sum rule, if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees. Which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. So I actually found out that OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. Therefore, OM, that is chord, that is line segment that exits from point O, that is the center of the circle, is perpendicular to FD. So we have perpendicular OM from the center of the circle towards chord FD. Therefore, we can implement here rule number 1, that is to say, because we have perpendicular OM that's perpendicular OM bisects chord FD, according to rule number 1. That is to say, FM equals to MD. So repeat again. OM that is perpendicular to chord FD, according to rule number 1, the perpendicular OM bisects chord FD. That is to say, FM equals to MD. Okay, actually it is rule number 1. FM equals to MD according to rule number 1. So we found out that Fm equals to Md. What is the value of Fm? From the domain it is very easy to see that Fm equals to Fa plus Am. Fm equals to Fa plus Am. Fm equals to Fa plus Am. And it is equal to Md. What is the value of Md? Md equals to Me plus Ed. Md equals to Me plus Ed. Md equals to Me plus Ed. In conclusion, we found out that Fa plus Am equals to Me plus Ed. But we have already found out that Am equals to Me. So here, Am equals to Me. Therefore, we can cancel out those two line segments because they are equal to each other. So we left only with Fa that is equal to Ed. Here, line segment Fa equals to line segment Ed. But we have already found out that Ed equals to 5 units. So we can write here that Ed equals to 5 units. And from this equation, Fa equals to Ed equals to 5. We will derive that Fa is also equals to 5 units. Here, Fa equals to 5 units. In the next step, we extended side BA by straight line until it touches the circle at point P. And then we implemented here the old rule, rule number 2. According to old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement the old rule number 2 in our drawing. Why? Because in our drawing we have chord FD that intersects with chord PB at point A. Okay? Repeat again. Chord FD that intersects with chord PB at point A. Okay, point A is the intersection point between the two chords. And therefore, we can, according to rule number 2, we'll get that Fa times AD equals to PA times AB. Okay, Fa times AD equals to PA times AB according to rule number 2. Fa equals to 5, AD equals to 18. PA is the missing line segment, so we leave it as it is, and AB equals to 6. In conclusion, we found out that 5 times 18 equals to PA times 6. Here we divided this equation by 6, and we got that PA equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15, so in conclusion, we found out that PA equals to 15 units. The missing line segment PA equals to 15 units. In the next step, I presented to you rule number 4, and we implemented rule number 4 in our drawing. What is the meaning of rule number 4? According to rule number 4, whenever you have two chords that are perpendicular to each other, you can use a certain formula because of the fact that we have two chords that are perpendicular to each other. We can use this formula. Okay, so here we have chord AB that is perpendicular to chord CD. Why? Because they create between them at the intersection point, that is to say it's point A, 90 degrees. Therefore, they are perpendicular to each other. Here OM is the radius of this circle that is defined as capital R according to our definition. Therefore, because of the fact that we have here two chords that are perpendicular to each other, the following equation is true. That 4 times r square, r is the radius of the circle, equals to ae square plus eb square plus ce square plus ed square. Again, 4 times r square, r is the radius of the circle, equals to ae square plus eb square plus ce square plus ed square. We can actually implement rule number 4 in our drawing. Why? Because in our drawing we have two chords that are perpendicular to each other. Here, chord FA, it is absolutely perpendicular to chord PB. Why? They have 90 degrees between them at the intersection point. And because of the fact that we have two chords that are perpendicular to each other, we can implement here rule number 4. So I repeat again. Chord FD is perpendicular to chord PB. Therefore, we can implement here rule number 4. And according to rule number 4, 4 times r square, r is the radius of this circle, will be equal to fa square plus ad square plus pa square plus ab square. Yeah, 4 times r square equals to fa square plus ad square plus pa square plus ab square. So 4r square equals to fa square. Fa equals to 5. So fa square equals to 5 square, that is 25, plus ad square. Ad equals to 18, so ad square equals to 18 square, that is 324, plus pa square. Pa equals to 15, so pa square equals to 15 square, that is 225, and finally plus ab square. Ab equals to 6, so ab square is 6 square, that is 36. So in conclusion, we found out that 4r square equals to 25 plus 324 plus 225 plus 36. So 4r square equals to 25 plus 225 is 250, and 324 plus 36 is 360. So in conclusion, we found out that 4r square equals to 250 plus 360. And 250 plus 360, it is equal to 610. So 4r square equals to 610. We divided this equation by 4, and we found out that r square equals to 610 over 4. We took a root out of this equation, and we found out that r, the radius of this circle that we are looking for, it is equal to the square root of 610 over 4. That is to say, r equals to the square root of 610, and the square root of 4 is 2. So we can take out 4, we can take 4 out of the root. And finally we got that the radius of this circle, the radius that we are looking for, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.